We already talked about this. Nobody's saying anything, so obviously we haven't talked about it yet. So module 15.4, compressors. I get a bad back echo, so I'm going to have to shut my speakers off. So unfortunately, I will not hear anything you guys say. Not that you're going to talk anyway. Module 15.4, compressors. In the gas turbine engine, compression of the air before expansion of the turbine is found in two basic types of compressors. Somebody in the meeting has muted me, so I've probably muted so hit unmute. So that way that person can stay awake and listen to this exciting lecture. You don't want to be. So anyhow, centrifugal flow compressors we will discuss first. And as we discuss this, centrifugal flow compressor engines as a form of propulsion, this is not a very common thing. These are things that were used in the 1940s and 1950s. However, centrifugal flow compressors, you will still find them in auxiliary power units, APU. So your APU on your 737 or A320, you will have centrifugal flow compression. So these engines are still being produced today, mostly as APUs. And you'll find some other engines have both axial and centrifugal flow compression, like the Allison 250. We have Allison 250 engines in things like our Angstrom and our Killer Fairchild helicopters. You'd also find these engines in the Bell jet engine, the Allison 250 engine. And we have some in our shop. You will actually get a chance to disassemble and disassemble turbine engines that have both axial flow and centrifugal flow in the compressor. Both types of compressors are driven by the engine turbine and are usually coupled directly through the turbine shaft. These are termed to be mechanically coupled. And an example of that would be this. Later on in the lecture notes, we will discuss the CFM56 engine. We will discuss the CFM56-5, that is an Airbus A320 engine. We will see Airbus A320 and 737. Both aircraft types have used the CFM56-5 and CFM56-7 engines. So the majority of time that we discuss engines on the Airbus and the Boeing, we will discuss the CFM56. And in our gas turbine lectures, when I get to lecture you guys again, we will discuss the CFM56 in great detail. Here we have our low pressure compressor. It is mechanically coupled to the high pressure turbine. Low pressure compressor, high pressure turbine. Our high pressure compressor is mechanically coupled. Sorry, let me just say that again. Our low pressure compressor is coupled to our low pressure turbine. High pressure compressor is coupled to our high pressure turbine. Need more coffee. This is our bypass fan. Our 80% of our thrust goes past the core of the engine. This is termed to be high bypass. High ratio of air that is bypassing compared to the air that goes through the primary gas flow. Primary gas flow, you go to the low pressure compressor, into the high pressure compressor, combustion chambers, high pressure turbine, low pressure turbine, then exhaust. You have 4 sections on your engine. You have compression, combustion, turbine, and exhaust. Axial flow, it's easier to see it because it goes through in one line, hence axial. Centrifugal compressors, which are primarily discussing here. We'll go back to them. Often things may happen in different orders, but nonetheless, you still have compression, combustion, turbine, exhaust. But it doesn't necessarily, on some of your engines, things don't happen in a linear fashion. Sometimes your compressor is in the front, your combustor is in the back, your turbine's in the middle, and your exhaust is in front of the turbine. That's a different story. We'll talk about that later. But the term mechanically coupled, I'm using this illustration to show mechanical coupling. There's a fan shaft. Your disc is bolted to the fan shaft. This shaft goes back, and your turbine, low pressure turbine, these 4 discs are bolted together. They in turn are then bolted and attached to the shaft. So this shaft with your low pressure compressor and fan, your low pressure turbine, they are spinning at the same speed. This is termed N1 speed, N1 rotor. Your N2 rotor, high pressure compressor, high pressure turbine, they are mechanically coupled. They're bolted together. This assembly of discs is called a spool, a compressor spool, like a spool of thread, a drum of thread, a spool. The spool is mechanically bolted, coupled to your single stage high pressure turbine disc. There's only one disc forming the high pressure turbine. So we have N1 and N2. RB211 has 3 separate rotors. We'll show you that. Your lecture notes have some of these illustrations, and they're a bit smaller and not as easy to see. So I'm going to use these illustrations to help you to see it a little bit better. There we go. That's what it is. This is a 3-spool axial flow engine. Not trying to confuse you because we were discussing centrifugal flow engines, but I'm trying to show the concept of coupling. So we have this shaft goes back, connects the low pressure turbine. Low pressure compressor is attached to the low pressure turbine. This is the RB211. We have this in the hangar. So our low pressure compressor is mechanically coupled to the low pressure turbine. The intermediate pressure turbine is attached to the intermediate pressure compressor. These are mechanically coupled. N1, N2, N3. Low pressure, intermediate pressure, high pressure. They all rotate at different speeds. So the speed your high pressure compressor is turning at is very fast. At takeoff power, you might be spinning at 12,600 RPM. Your fan, on the other hand, would probably be turning around 3,000 RPM. It doesn't have to turn as fast because the blades are nice and big. They produce lots of thrust. Intermediate pressure compressor would be something in between your LP and your HP. So perhaps it's spinning at 7,000 RPM. This is spinning at 12,600 RPM. When we get into centrifugal flow engines, Rolls-Royce did try to make a 3-stage, an N1, N2, and N3 centrifugal flow engine. However, the difficulty is in controlling the speed of your high pressure compressor section. By controlling the fuel flow, the amount of fuel that we put into the combustor on this engine, the RB211, we can very efficiently control the speed of the high pressure compressor. On the centrifugal flow engines, Rolls-Royce had difficulty in maintaining the speed of the centrifugal flow compressor. And then you have an overspeed condition, and they had structural failures on some of their test engines. Also, you'll notice the diameter of our HP compressor. It's smaller than that of the LP compressor. With centrifugal flow wheels, to be efficient, they still have to be fairly large, but your tip speed, the speed of the compressor, is too high. then it is not efficient in terms of compressing the gases. So with centrifugal flow compressors in production, they've only had two-stage engines. This axial flow, 3 stages, is the most anybody's attempted. Nobody's made a 4-stage compressor, 4-stage turbine axial flow engine. As it was when Rolls-Royce developed this engine, it bankrupted the company and the government had to assume control of Rolls-Royce. The government saved Rolls-Royce. This engine was being developed for the Lockheed L-1011. This engine had gone out of production. That would have caused considerable delays for the L-1011's delivery. And they would have ended up using probably General Electric CF6 series engines. And then the CF6 series engine is not efficient. The fuel efficiency of this engine has been its prize reason for existence. We had RB211 engines on our 757s at Continental Airlines. We could fly nonstop from Newark all the way to Stuttgart, Germany, Stockholm. You could go to Copenhagen. You could go to a lot of cities that the Pratt & Whitney engines could not fly to because they burn a lot more fuel. Only 2 compressors. With the 3 compressors, each rotor turns at its best efficiency, peak efficiency. This engine is a masterpiece of engineering. It is a fantastically reliable, dependable, robust design, very fuel efficient, which is terrible because I worked for General Electric, the competition, and our engines with only 2 rotors, N1 and N2, our engines are not as fuel efficient. Therefore, you have shorter range with Rolls-Royce or Pratt & Whitney designed engines than you would with this. With General Electric and Pratt & Whitney, you have lower range. RB211 has higher range because it's more efficient. Since each one of these rotors can spin at its most efficient speed. So the fuel is burning here in the high pressure compressor, high pressure turbine. This is rotating. This rotates first when we start the engine. Exhaust gas coming out of the high pressure turbine hits the blades on the intermediate pressure turbine. Gets the intermediate pressure turbine spinning. This in turn then is driving the compressor. Exhaust gas that passes through both turbine wheels then reaches the low pressure turbine. LP turbine rotor spins, thereby spinning the fan. The only reason that turbine wheels exist is to mechanically drive compressors, or in some cases, your turbine wheel will drive a gearbox, drive the accessories, or you'll have a free turbine wheel that'll be connected to a gearbox so you can drive a propeller, a helicopter rotor through a gearbox transmission. So the reason your turbine blades and turbine wheels exist is to drive compressors, provide energy to drive your high-speed external gearbox. You'll have your generator on the engine. You'll have fuel pumps, lubrication pump, oil pump. You'll have your starter on there. Starter will rotate a high-pressure compressor when you're trying to start the engine. So when you're doing borescope, you can rotate the high-pressure compressor, high-pressure turbine. This is what you can rotate through the starter drive shaft. IP compressor, you can't rotate that way. You have to actually reach through here and actually physically push the blades with an adapter tool, which means when you're borescoping, you can't get the blades to go by at a nice, even, slow pace. Blades tend to jerk around a bit. That's another story. Getting back to our lecture notes then. So we just diverted it a little bit so we could explain that compressors are driven by the engine turbine and are usually coupled directly to the turbine shaft. So basically, you mechanically couple your turbine and compressor. Almost always it's directly through some kind of a shaft or through some kind of a structure. Like you can have something where it's not necessarily a shaft, but you can have the aft end of your spool of discs, your assembly of discs. You can bolt them directly to something also that is then going to attach to your turbine wheel. So on the RB211, you have a lot of areas where it's hollow, and then you have something else that passes down to the center of your compressor and your turbine, and it's going to be connected to another turbine and compressor. So in the RB211, you have one shaft that is connecting your low pressure fan, low pressure turbine. That has a shaft. Then the other structures are less shafts than just being big hollow drums. But then the fan rotates, then the IP compressor rotates at its own speed, HP compressor spins at its own speed. You'll be able to look at some more cross-sectional diagrams and understand how the RB211, how do you have 3 stages, and how do they all turn independent of each other. You could also even have an engine like the RB211 where some of the rotors turn clockwise, some of the rotors turn counterclockwise. And since we're aerodynamically coupled, there's no mechanical connection between N1, N2, N3. It really is completely arbitrary which direction the rotors actually physically turn. Some manufacturers have gotten it to where they have some rotors that turn this way, other rotors turn the other way. I think they're thinking that if you have a single engine system, you have an engine failure, you have less forces that might cause it to be a bit more difficult to control. I don't know why anybody would really care which direction they turn, but sometimes some of the engineers have their own thoughts. That perhaps N1 needs to turn clockwise, N2 can turn counterclockwise. Might help for controllability in single engine operation. Centrifugal flow compressor is a single or 2-stage unit with an impeller which accelerates the air and a diffuser which produces the required pressure rise. The impeller rotates. The impeller spins, it rotates, it's your rotating compressor. The diffuser is part of a stationary assembly, stationary diffuser case, and it does not rotate. I'll show you some examples in a little bit. Axial flow compressors are multi-stage units with alternating rows of rotating rotor blades and stationary stator vanes. Some of the stator vanes are fixed. They don't change angle. You have others that have actuator will change the angles of the variable stator vanes, which angle that they face into the airflow. So your rotating blades accelerate the air. Then your diffusers, they diffuse the air, get the required pressure. So you slow the air down. So your rotating blades accelerate the air. Stationary vanes decelerate it, obtain a pressure rise. They say diffuse the air. Diffuse the air. So you're trading off your velocity, turning it into pressure. Sometimes on smaller engines, like the Allison 250, you have an axial compressor and a centrifugal compressor. In the case of the Allison 250, these are actually physically bolted together in one unit. They turn together. You have several stages of axial compression. And at the back, you have a centrifugal compressor. Centrifugal compressor will take the airflow and now make it head outward in a radial direction from the center of the engine. The reason you do this then you now go into some ducting that then takes the air outside of the engine case You go to the very back of the engine, then you come back in, you turn around, and you go into a combustion chamber that's mounted at the back of the engine. So you do your compression, combustion, then you come into a turbine, two turbines, and you go out the exhaust in the middle of the engine. You'll see that when you work on Allison 250. It's much easier to see it in person. So they call that a reverse flow combustion chamber. Centrifugal compressors are easier and cheaper to develop and manufacture. They're good for smaller engines because they're smaller in size. Mostly we're saying about their shorter engines. They tend to be larger in diameter than they would be if they were axial flow, but they are shorter in overall length. So a lot of your APUs are going to be, you want it to be shorter. So they use the centrifugal flow compressor because it's shorter and it's cheaper to manufacture, cheaper to develop. Centrifugal flow engines are robust construction, resilient to foreign object damage. They can take a lot of abuse. You can get a lot of nicks and dents in the big impeller, and it'll keep going. They don't break as easily as you can break a compressor blade. Engine surge is not critical. It's a little hard to get surge in a centrifugal flow compressor, but it produces a short compressor section, so you can have shorter overall engine length. Readily accepts ram airflow. So if you have an APU in the back of the airplane and your ducting on the outside brings the air, comes into the APU, that you're starting an APU in flight in the 737, you're subjected to ram airflow because you're flying at Mach 0.82. And APU has to be able to start in flight on 737s. They have to do a cold soak APU start. So 41,000 feet is the highest altitude that APUs are reliable to be able to start on the 737-800, which is why you're limited to 41,000 feet. And they say low starting power requirement for centrifugal flow compressor. However, whoever wrote this in the UK, they never tried to start a centrifugal flow engine. It's actually really, in truth, it's the other way around. You have the great big impeller, and you have to try to get that thing to spin. There's a lot of mass, and your starter is very powerful, and the starter can put in so much torque that there's a spline shaft in between, and starter shafts break all the time on 233s. Usually you carry two of them as a spare, and unfortunately then the starter is very heavy. You have to remove the starter and change the spline shaft. So how you try to overcome that is you use something called soft start. So you don't throw all of the amperage on the starter all at the start. You just throw a little bit of amperage. So you put a little bit of torque first, and then there's a timer circuit that gradually, it slowly picks up more and more power until finally you're spinning at the full power that you need, at the speed that you need to have to be able to accomplish a good engine start. But if you threw all the torque in it all at one time, you'd just break the shaft and the impeller wouldn't even move. Centrifugal compressor disadvantages. Your pressure ratio is governed by the tip speed of your impeller. So if you made a larger impeller, your speed's going to be larger because larger diameter, your tip speed relative to the casing, it's going to be faster. So this limits how big you can make it, how fast you can spin it. You have relatively low overall maximum compression, 15 to 1 with a dual stage engine. It's about the most you're going to see. We have a little Rolls-Royce engine in the shop that we don't do anything with. It's not a cutaway, and I think that one has 2 stages of compression with centrifugal compressors. So 15 to 1 is not a lot of compression. You'll find your axial flow engines, they've got developmental engines right now. You can get 45 to 1 compression, and some of the more modern designs are coming out with. You're limited to only 2 stages. Rolls-Royce tried to make a 3-stage centrifugal compression engine. And the developmental engines had far too much trouble. The performance wasn't good. They couldn't control the speed of the highest pressure compressor section, so they would have a lot of damage, have catastrophic failures. If the speed were allowed to run away, you get up towards 80,000 RPM if you don't shut it down. And you can't regulate the airspeed of your third stage of compression, it'll structurally fail, and the tip speed makes it inefficient if you're going too fast. So in production, you're limited to only 2 stages of compression. You end up with an engine that's much, much larger in diameter for the amount of thrust that you get. If you had a smaller axial flow engine, you could have an engine this big. J85 engine's about this big around. J33 engine's about this big around. And J33 puts only about 4,200 pounds of thrust, and a J85 puts out 2.5, 3 times the amount of thrust. You have directional changes in airflow. Your airflow doesn't go through in an axial direction. Air comes through the press, goes out radially, turns around 90 degrees in the diffuser, goes through the combustor, goes through the turbine. These directional changes in airflow causes less efficiency due to air friction. You have high specific fuel consumption. You burn a lot of fuel for every pound of thrust that you develop, so they're very fuel inefficient engines. And when you have turns in between stages, the airflow turning around, and this causes losses in efficiency. The advantages of an axial compressor engine are you can have pressure ratios of 7.1 and upwards. Some of the more modern developmental engines are talking about having pressure ratios of 45 to 1, which is an incredible amount of pressure. Most of the time, you'll see later on, most of the pressures in the engines that you're going to be working on will be 178, 180 psi at the back of the high pressure compressor section. That's usually the actual pressure inside the engine that you'll see in most of your engines that you'll be working on. So you can get a higher airflow for the same frontal area, same diameter of the engine. You can just keep adding extra stages. In theory, you could have a 30-stage high-pressure compressor. In reality, in production, you'll see usually 16 stages or less on your high-pressure compressor. Rolls-Royce Avon, which we'll show later, Rolls-Royce Avon has 15 stages, but actually they have a stage 0. So it's 16 total stages. You have improved specific fuel consumption for a given thrust. So this means for your takeoff thrust, you're burning less fuel to achieve that thrust than you would if you had a centrifugal flow engine. The straight airflow allows high ram efficiency. So for a high-speed aircraft, you would not be able to use a centrifugal flow engine. If you want to go supersonic, you're using engines that are axial flow. There are no supersonic aircraft that fly which have centrifugal flow engines. And you have small frontal areas with a smaller aircraft, more fuel efficiency, lighter weight structure. Airplane like my T-33, it had to be very wide, the fuselage, to be able to accommodate the centrifugal flow engine. Axial flow compressor disadvantages. Very high cost to manufacture. 50% of the cost of your brand new 747-8. $260 million airplane. Half of that cost for the 4 engines, the CFM56-8. Half the cost of the airplane is the cost of buying the engines. Jet engines have a very high cost to manufacture. The engines are very susceptible to damage if you have surge. Surge is where the engine's pulling air through. All of a sudden it decides, the air decides it wants to go back out the front of the engine while your compressor is rotating several thousand, up to maybe 12,600 RPM. You don't want the airflow to try to go back out the front of the engine, because now it takes that rotor and tries to stop it in dead stop from 12,600 down to 0, and then try to make it run backwards. Meanwhile, other air is trying to come forward. Engine surge is very detrimental to the compressor in particular, but detrimental to the whole engine. So we want to control the airflow so we do not get surge. Compressors are easy to damage by foreign objects. This is not correct, really. Slow to accelerate. I don't know why they would say slow to accelerate. All compressors are slow to accelerate. But the slowest one to accelerate is centrifugal flow, because you have this huge impeller wheel getting it to spin up, accelerate. T-33 jet, which uses centrifugal flow engines. I know of 2 aircraft that crashed. One of them used to be mine. The pilot had wind shear, went to try to get takeoff power to make a go around, and the plane just sank into the runway, ripped the landing gear out of it, and basically destroyed the airplane. And of the 16 jets that were part of the auction, I bought 2 of these jets. Out of the 16 aircraft, 2 have been destroyed in circumstances where people tried to make a go around, take the engine, go to takeoff power, and centrifugal turbine, centrifugal flow compressor. It's so big, it's so heavy, it does not accelerate. It would take up to 14 seconds to go from idle to full takeoff power with the centrifugal flow engine. Axial flow compressor will get to that speed much faster. But all jet engines are slow to accelerate, but an axial compressor engine is much faster than a centrifugal flow engine. Axial compressors are only efficient at a specific RPM. But when you have 2 or 3 separate compressors in an axial flow engine, like RB211 has 3 compressors, low pressure, intermediate pressure, and high pressure, each rotor can turn at its best efficient speed. Whatever speed is most efficient for that rotor, it can settle into its own speed. And this helps the RB211 be more fuel efficient because it has 3 separate rotors. General Electric's engines are not as efficient fuel-wise because it only has 2 sets of rotors. So axial compressors are only efficient at a specific RPM. And again, they say high starting power requirements. That makes you think that a centrifugal flow compressor is easy to start. Centrifugal flow engines are much harder to start, again, because the mass of that impeller is so big. Trying to get the engine to start, you need more power. But for axial compressors, when you have 2 compressors, 2 separate split compressors, then you only have to rotate your N2 or N3. Once it starts, it then aerodynamically couples to the other stage. So if you had all of the stages all bolted together as one gigantic rotor in an RB211, all that mass all together, it would be very difficult to get that engine to start without breaking the starter shaft. To get all of that mass to rotate all at once, that would be very difficult. So that would be a high starting power requirement. You had to start the whole thing instead of just the N3 spool. So we have all of this text and no corresponding pictures. So we have to repeat some of this later on as we look at the pictures, so then it kind of sink in. At least you guys, if you have the book, then you have the text here, you have the picture here. So as you're going through, you have the text and the image to look at. So here we have the 2 different types. You have a 2-stage centrifugal flow engine. And then this one is probably Rolls-Royce Avon, in which case it would be 16. Most of these illustrations in the first part of your book appear to have come from Rolls-Royce, which is nice because we have 2, if not 3, of these engines. We might have this engine as well in the shop, but we don't have it as a cutaway. So your air comes in through the front, goes into your impeller, gets compressed, velocity increases. But we don't want high velocity gas in our compressors. We want high pressure. So with your combined gas laws that you studied in physics, You realize if you have a combined gas, you increase your pressure, you'll get an increase in temperature. So what we do is we take the velocity, slow it down, but we increase the pressure. So we trade off velocity for higher pressure and higher temperature. First stage impeller wheel, second stage impeller wheel, combustion chamber, single turbine wheel here. This turbine wheel is mechanically coupled to this compressor impeller disc. These are physically attached to each other. This one
Teacher,
physically attached to this one looks a little bit orange.
teacher,
Temperatures. A little bit cool in the front. It's green here, and it gets a little bit orange, orangish yellow. And as it comes back here, it's trying to be an orangish red, then a red, then a red, orange. So increasing pressure, increasing temperature. More pressure increase, more temperature increase. And then when the air comes out here, then you're at a higher pressure and higher temperature, which is good because you want the flame that is already going inside this combustion chamber. You want the flame to stay burning without the use of a continuous ignition system. Turbine engines only use ignition for starting. Once the engine is started, you do not want to use the ignition system continuously in flight. Your igniters will burn out. They will not last as long. If you fly through heavy rain, thunderstorm, or if you're coming in for landing and you really want the backup in case you think maybe the engine might try to stall, you turn on the ignition as a backup system, then that's fine. But once the engine has started, you do not need the igniters anymore for the engine. In theory, you don't need it. The engine will keep running because your higher pressure, higher temperature, when it comes into here, you already have the flame going. The fuel auto ignites. It's burning. That's back through. You don't need to. It's not like a reciprocating engine where you have to have a spark plug that you have to have it continuously keep firing, keep the engine going. So you go through your first stage of turbine. Then these two turbine wheels are bolted to each other. They're attached. And then they have a shaft that then passes down through this one and comes out, and it's attached to this impeller. So this impeller is mechanically coupled to these two turbine wheels. So this high pressure compressor and turbine, they will spin very fast in comparison to these other ones. Rolls-Royce had a developmental engine. They tried to do the same thing here with 3 impeller wheels. And then with the third impeller wheel and turbine wheel, they found that it was very difficult to keep it from overspeeding and having any structural failure. It weighed a lot more, it was more expensive to manufacture, and the amount of thrust that they could have gained out of developing and deploying these type of engines, the amount of thrust gained wasn't really enough to justify the expense of manufacture, the weight of the engine, and the risk of having an overspeed and therefore catastrophic uncontained failure of your turbine and compressor section. Since Rolls-Royce did this work, though, in trying to figure out how to make a 3-spool N1, N2, N3 engine, they tried to make this centrifugal flow engine more efficient. Their engineers then had a lot of advantage over General Electric's engineers and Pratt & Whitney's engineers. American engineers didn't bother to try to make 3 compressor spool engines. So when it came to develop axial flow engines, Rolls-Royce already had the mechanical mind to think of making a 3-spool, 3-rotor axial flow engine. And the development of this almost bankrupted the company, but in the end, the British government bailed them out, and they were able to save the company and then develop an engine that has 3 separate rotors in axial configuration. So this right here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
17 blades. So this illustration is probably Rolls-Royce. General Electric, pretty much 16 rows of compressor blades is as much as Rolls-Royce attempted. General Electric only has 16 rows in their engines. 14 to 16 rows of compressor blades. So this is probably Rolls-Royce Avon. Looks like it's a Rolls-Royce illustration. Some of your other illustrations in here are Rolls-Royce illustrations, and we have a factory cutaway instructional engine in our shop where you can look inside and you can actually see this engine. So what we have is we have a convergent duct. We have a large area at the front of the compressor, and it's getting smaller and smaller as we go to the back. And then we end up with blades in the back that are about this tall, blades in the front that are about this tall. So what happens is, as the air is going through here, the rotating blades are increasing the pressure and temperature of the gases. Let us get some echo so you will hear that better. We are increasing Sputnik effect. I want you to pay attention. We are increasing temperature. We are increasing pressure. We are not increasing velocity. The purpose of the compressor is not to increase the velocity of the gases. Remember this, because this is probably one of the things people get wrong the most of the time on oral practical job interviews, exams for licenses, exams for school. Your airflow, the velocity when it comes into the front here, it is neither the intention. You don't desire for it to happen. You could develop the engine to produce lots of velocity in the back of your compressor, but you don't want that. You want to increase temperature and pressure, but primarily you're increasing pressure. And the way you do that is each one of these sets of blades does accelerate across from the front of the blade to the back of the blade. You do get an increase in velocity. But then as you go through your stators, the way you design the stators is by divergent duct technology, is the air will slow down, the pressure increases and your temperature increases. So if we put in temperature and pressure monitors at each stage, you'd be able to monitor the fact that the temperature and pressure is increasing at each stage. However, if you're measuring velocity here, you would not find that you have an overall net increase in velocity. There is a picture down here a little bit further that shows this. So they have this little diagram right here on page 19 of your notes. I've made it a little bit bigger version of the picture so you can see it. It's on the very bottom. It's a little harder to see on your lecture notes because it's a small illustration. But you'll notice this curve, our curve for velocity, that we do see an increase in velocity as we go along from the front of the blade to the back of the blade. We do have an increase in velocity, but as we go through the stator, we slow the gas back down again. By decreasing the velocity, we increase the pressure and the temperature. We want higher temperature air at the back of the compressor. This will aid in ensuring that the combustion process will continue without having to use igniters. But we want the pressure. That's our number one goal of the compressor, is we want the pressure to come through. In the combustion process, you'll burn about 20% of the air that goes through your compressor will be used to actually mix with fuel and create combustion. The other 80% of your air as you go through the combustion chamber area, use that to route through the outside, through little slits and holes of the combustion chamber. You want to use that higher pressure air. Temperature is a bit warm, it's a bit hot, but it's not as hot as the flame. You're using that air to center the flame down the center of your combustion chamber. You don't want the flame, the burning fuel, you don't want the burning fuel to come into contact with the metal of the combustion chamber lining. The metals in the combustion chamber, I think about 850 degrees Celsius, you'll start cracking, damaging, deforming your combustion chamber liners. But your fuel's burning at about 2,100, 2,300 Celsius. So you do not want the flame to contact the combustion chamber liner directly. So again, your compressor, you increase the velocity with the compressor blade, but then with the stator, you decrease the velocity back down again. So your velocity is bouncing up and down, up and down. But the net result is at the back, whether it's 14th stage, 11th stage, 16th stage of your compressor, your velocity at the back of the compressor is the same as what the velocity was at the front. As you're flying through the air, if you're going 600 miles per hour, air is coming into the engine, your velocity back here is the same as it is here. But your pressure has gone from 14.7 psi at sea level. You're at about 170, 180 psi at the back. Everybody confused? I'm sure you're confused. Just to do an audio check, I want to see if anybody is actually awake. I'm going to ask a question and somebody will give me an answer. Question is,
When is break time? Is it break time yet? Nobody is answering. So we will continue. Is anybody awake?
Yes.
Yes. When's break time? 2:10?
Yes, teacher.
210,
What
210.
time? What time is break time?
210.
2:10. Okay, so you're paying it. I see somebody's awake. So you guys never heard about compressors before, right? Your director didn't tell you about compressors? No? Yes? Okay, now go back to compressors.
echo if I do that. So anyway, as we were saying before, we have this other illustration that you guys have, I think on your page 17, where it shows your air coming past your inlet guide vane, first stage rotor blades, first stage stationary vane, second stage rotor blade, second stage vane. Then you have bleed air. Bleed air, you take the air off for things like anti-icing, pressurizing the airplane. You can start the engine on the other side of the airplane using your bleed air. This diagram here, this picture, also would be a Rolls-Royce Avon cross-sectional diagram, and I've got some better pictures of Rolls-Royce Avon I will show you. So in this case, we have one compressor spool that is attached to one compressor rotor. We have three turbine discs but they are attached to the compressor, mechanically coupled. Right here, behind the compressor, on the Rolls-Royce Avon, we have an interesting feature where we can reach inside the engine and we can do a quick disconnect. We can then remove the single-stage turbine as one unit. However, because our turbine has got stators and rotors, not just one single disc, we would have to unbolt the flange. We'd have to remove the entire module, stators, rotors, everything, bearings, everything. The whole thing would have to come off as one big module, but we could change the turbine module in a hangar. If engine's on the airplane, I don't think you can change it on wing because I think your aft engine mounts attached to the turbine section on this engine. These would be your combustion chambers. There are 8 cans, burner cans, combustion chambers on the Rolls-Royce Avon. So the cans are arranged in a circle like the sun and the earth. The earth goes around the sun. That's annual, 1 year. So annular, the 8 cans go around in the circle. 8 cans for the combustion chamber on Rolls-Royce Avon. So our picture here showed centrifugal flow compressor, axial flow compressor. Centrifugal flow compressors have either a single side impeller or a double side impeller. Sometimes you have a 2-stage single-sided impeller. So what they're talking about is these are 2 stages. They're both single-sided impellers. 2-stage, single-side impeller. Only a single path of entry for your gas coming in, your air coming in to be compressed. This is not dual entry, this is single entry. My airplane that I used to have 2 of these jets, T-33 jet. It had dual entry. So in this picture, they talk about single stage dual entry. So we have one rotating wheel that the air will come in from the front, and then we have air that gets drawn in from the back. And they'll have screens on the side of the engine. The air actually comes in kind of through the top of the engine casing and goes into it. There's no inlet at the front of Rolls-Royce steam engine. The air doesn't come through the front of the engine because they have the accessory gearbox on the front of the engine. So with this, the air actually comes down through 2 sets of screens, goes down, gets compressed, and then comes up and goes through the diffuser section. So single stage, single entry. The air in the one that they showed us earlier, the air comes straight into the engine. On this type of engine, though, if you look at the curvature of this, the air is actually coming in down through here, comes into here. So. I've turned the picture sideways so we can see it a bit better. So when the engine is operating, the air comes in through 2 inlet screens, comes down in through here. The air is actually coming down into this part and then gets accelerated and compressed and then goes up. It's a big wheel that's spinning. It's made of 3 different pieces. One piece at the bottom here, then this middle piece, and this top piece. It's easier to manufacture these curved sections if it's made in 3 separate parts. So they're bolted together, but it all rotates together as one assembly. Your diagram doesn't have something showing that there's a split between these 2 parts. There should be some kind of a continuation of this line here, so you see that there's a different component at the top and at the bottom. Your illustration doesn't show that. So you have a split here. So there's 3 separate pieces. A little hard to see it here, but there's a split right here between these, and the split here. So the air is coming in from outside the engine. It comes in through here, gets compressed, then it gets spun through, gets spun up and out. So the air comes in outside, makes a turn, gets compressed, makes a 90-degree turn in this section right here, comes up, makes another 90-degree section turn here. So overall, we're making one 90-degree turn, a second one, and then the third one. There's 3 changes of direction of our gas. A little less efficient. Our diffuser, these are diffuser vanes up here. The air comes out of the impeller wheel. They talk about the tip speed of the impeller wheel. They're talking about the speed at which this is rotating. This piece here is rotating. And then you have a gap between here and the diffuser case. They say you want to have that gap at a minimum. That is a manufacturing and overhaul function. Even though this is an ex-military engine, in the US, the FAA does not want you to take this part apart. You should not be getting into this part of the engine. You're supposed to send this to an overhaul facility that's licensed to do this type of work on these engines. People think because it's experimental, they can take the compressor section apart, but they don't have the tooling, training, and facilities or spares to do that, so they shouldn't do that. You can, however, remove the turbine wheel and this turbine shaft. We can uncouple it right here. There's a coupling right here. Your lecture notes will discuss this coupling. You reach down inside here, you push down a pin, and then you can slide and remove this turbine shaft and turbine disc. You guys are going to remove your turbine disc and shaft on the J35 engines in the shop. So this is a single stage, dual entry centrifugal flow compressor. The air comes in, 2 screens. There's little mesh screens. They'll stop large pieces of fog. They won't stop small pieces of fog, like rocks, safety wire. Won't stop them. If a bird gets sucked into the back of the engine, it'll catch that. It'll catch big things. But the mesh is about 1/2 inch, so smaller objects could get through here. These impellers, though, if you get fog damage, it's not as likely to fail, not as critical, not as susceptible as a axial flow engine. The air does not flow in from the front of the engine and go through it because we have an accessory gearbox mounted on the front of the engine with our starter. It's an electric starter. It has a cooling duct to blow some cooling air onto it, but this is an electric starter. These are the igniter boxes, 2 igniters. One of the igniters goes to the very bottom burner can. The other igniter goes to the top of the engine, top burner can. There are 9 combustion chambers on this engine. Rolls-Royce Avon, there are 8. Avon is nice because the igniter plugs are not on the bottom 2 combustion chambers. On this engine, the combustion chamber on the bottom, fuel can collect on top of the bottom igniter and then it doesn't work, which means you're trying to start the engine with only 1 igniter plug working. This makes starting these engines a little harder, and the temperatures can exceed the maximum if only 1 igniter plug is working. The fuel has to jump between interconnection tubes from chamber to chamber and get the engine started. We will show you that picture a little later. But in the meantime, this is what your turbine wheel looks like. They discuss the fact that you can uncouple this and remove the turbine wheel. So what happens is there's a plunger in here, and then you rotate the wheel so that these locking lugs will then pass through this assembly to be able to remove the turbine shaft. So this stays in the engine, and then the shaft itself with the turbine disc, you can remove that. You can change the blades in the field. There'll be limitations on how many blades you can change in the field because of weight. So you want to get a blade that weighs the same. Also, another thing which is harder to measure in the field is you also want to measure how long the blade is, because if you put in a brand new blade and it's a little too long, it'll rub into your stationary case, causing wear and increasing the tip clearance between the other blades, makes your engine less efficient. In an overhaul shop, we would put all of the blades on this disc, and then we would put them on a grinding machine. We'd take a machining tool and we'd measure how much we wanted to grind, and then we'd go in with a grinder basically. And as the disc is spinning, we would just grind the tips of the blades so that they all met the dimension that we wanted to have prior to installing a brand new turbine wheel with brand new blades. Before you put that in the engine, you had to get the distance from here to here, be very precise. So again, this is a centrifugal flow engine, centrifugal flow compressor, Rolls-Royce RB41 mean engine. Single stage, dual entry, centrifugal compressor attached to a single stage turbine wheel. Mechanically coupled, so you're mechanically coupled together. And we can disconnect this here by reaching down to one of the burner cans. We take the burner can off, we reach down to the side of the engine, we can disconnect this and slide it out. Rolls-Royce Avon has the same thing, so we could remove our turbine on the Avon. Here you don't have any stationary blades behind, so when you pull the turbine wheel out, you can remove the turbine wheel without further disassembly. Avon, we have stators and rotors and stators, and so we would have to take the entire module off. We'd have to unbolt all the flange bolts and then slide the entire unit off as one large module and then disassemble it. So our centrifugal flow compressors have a single or double-sided impeller. So I showed you the pictures where we had a double-sided impeller. Your illustration that's on the previous page of these lecture notes shows 2 stages of single-sided impellers. So the impeller is supported in the casing that has the ring of diffuser vanes. So that's your stationary part of the engine. And if a large volume of air is needed, a dual entry compressor can be used. In the case of the Rolls-Royce RB41 mean 10, you have a dual entry compressor. You have 2 sets of springs, the air comes down into the engine. It's a dual entry compressor because you need a large volume for this. It's a fighter aircraft. So one major problem of the double entry compressor is the difficulty in designing inlet ducts to supply air to the rear part of the engine. In the T-33, actually, the entire engine just sits in a large part of the fuselage, large compartment. The air comes into the ram air ducts on the sides of the fuselage that go past the pilots, and then the air just fills this cavity. And then actually between where the cockpit ends and where the engine begins is probably a good 3.5 or 4 feet, very large area. So the air is not ducted directly to the engine, it just fills that cavity. And at high takeoff power, the inlet ducts on the side of the fuselage, on the original aircraft, actually they had the ducts, the fuselage crushed and collapsed. Quad broke off, went into the engine, destroyed the engine. They had to design relief doors, pressure relief doors that are spring-loaded on the top of the T-33. When you see it's a high takeoff power, these doors will spring open. Air comes down to the top of the fuselage, and that's how the air is getting to the rear part of the engine primarily, and then air coming through the front, it gets into the front of the engine as well. So, but if you wanted to design an airplane where you brought air and had a duct, then you'd have to have ducts go around the outside of the engine and back towards that part of the engine. But the majority of aircraft just overcame that by not having ducting to go to the back of the engine. So the dual entry impeller is used. The airflow to the rear side is reversed in direction, and a plenum chamber is required. They don't have a picture to illustrate that very well. We'll try to look at this engine again and see if we can make that a little bit clearer. So in your impeller, they have a 50% rise of your pressure, of your overall pressure comes from the impeller. The other 50% comes from the diffuser. So your pressure and velocity increases. You take that velocity of the air and convert that to pressure. So you slow the air down again, slow the velocity down, you end up with an increase in pressure. This is what I was showing you before. Dual entry, single stage, centrifugal flow compressor. They were saying that if you wanted to route air to come back here, you'd have a difficult time making ducting. As you see with the diffusers being around this area, it actually making ducting would be difficult. But operationally, we don't take any ducts and route it back into here on the engine. In reality, we just have an entire compartment that has a large volume of air being fed into it through these inlet ducts on the side of the airplane. But these ducts cannot supply enough air to operate this engine full takeoff power. So on the top of the aircraft here, above this letter P, there'll be spring-loaded door about 18 inches long, about 7 inches wide. There's one on each side of the fuselage. These doors spring open if there's a negative pressure inside the fuselage. Go to takeoff power in the engine. There's not enough airflow going through here to supply the engine, so then these spring-loaded doors in the top allow air just to go into the top of the fuselage to feed the compressor. So, single stage, centrifugal flow, but dual entry, 2 paths of entry for the air. This is not the best picture in the universe either, not as clear, but it shows that we have our dual paths of entry of the air. It's compressed. Tip clearance here is, they say that this is a defining feature in terms of how you build up the engine, how efficient it will be. You need to have a minimal clearance between the tip of the impeller and your diffuser case. The air goes up, comes to these diffuser vanes. The diffuser vanes slow the airflow down, so you trade your velocity, turn it into pressure. Your air will then flow into the combustion chamber. 20% of the air goes through the area with the fuel nozzle. The other 80% of the air routes around the outside and then comes to all of these cooling holes. There's also a row of very small, fine cooling holes here. The air coming through here has a lot of pressure, so it will force itself into here, and it creates a jacket of air for cooling and also to keep the flame centered, because if this flame came into direct contact with a combustion chamber, it would burn through in a few seconds. So 80% of your air that goes through the combustion chamber is not used for combustion. It is used for cooling and for keeping the flame centered. The combustion gases will then come back and it will hit a stationary vane. These are solid metal. This is the one part of the engine that gets subjected to the highest temperatures. Subsequently, on all jet engines, this is the part of the engine that is most likely to fail because of temperature-related stress. There are high-pressure turbine nozzle vanes. High-pressure turbine stationary vanes, they take the airflow from the combustion chamber and then they direct the airflow so it will hit the rotating high-pressure turbine blades. General Electric, in their industrial engines, they like to call them buckets. In their early military and industrial engines, and commercial aircraft engines, they would say that these blades are buckets. Sometimes you will still find the term in in General Electric engines, they still call these buckets. However, most of you are going to call them blades. These high pressure turbine blades are one piece. There's no cooling holes. No air passes through these blades. They are not hollow. Stationary high pressure turbine vanes are solid. They are not hollow. There's no cooling air. CFM 56, this high pressure turbine stationary vane, they are hollow. They are filled with pressurized air coming from high pressure compressor. High pressure compressor air is hot, but it's not as hot as the combustion chamber gases. So it helps to provide a cooling jacket, a cooling film of air around these parts, conducts the heat away from them, keeps them from overheating and cracking. The turbine blades on a CFM 56 are also hollow in the first stage. First stage is they're hollow. Cooling air will be directed up into the disc, into the blades, and cool the blades off. It's actually not directed into the disc. The disc is solid, but there's kind of a jacket of components around it. The air gets trapped and it gets directed up, goes into the blades, and cools them. We will see if we have enough time to go into that in detail during subsequent lectures. You're lucky because we have some CFM 56 in our lecture notes. Since it's in our lecture notes, that means we can talk about CFM 56. And if we want to get to where we have this page, alright. But that's not the one we want to see. We want to see much better. So I know you guys have a break in a few minutes, but really quickly we will discuss power plants. We'll discuss how you would work on a Boeing aircraft. This is Boeing Toolbox Remote, Toolbox Offline. This is an application where we have all of the manuals required to work on a Boeing 737. Aircraft illustrated parts catalog in ATA 71 through ATA 80. They will have components that the engine manufacturer feels that could be changed without having to go to an overhaul facility or some kind of a shop. You could actually change these components on the flight line at the gate. So then engine components that are covered by tasks that can be done at the airline by the average airframe and power plant technician, you will find illustrated parts catalog, AMM, Aircraft Maintenance Manual Part 2, ATA 70 through ATA 80, that block of chapters. They get covered in the AMM Part 2. Remember, AMM Part 2 is your actual manual. AMM Part 1 is not an aircraft maintenance manual. So if you look at the history of what we were doing earlier, this right here is AMM Part 1. You notice it says Maintenance Manual Part 1. If you were out working on an airplane, a real airplane, and somebody came by and asked what you are doing,
You would not want to have AMM 1. You want to be working with AMM Part 2, not Part 1. So this is showing engines starting component locations in the flight compartment. And its description and operation. It is not how to fix the airplane. So SDS system description section of the aircraft maintenance manual. Maintenance manual part 1 is not legal for work on the airplane. You would want to use AMM part 2. So ATA 77 is engine indication. 7721 exhaust gas temperature indication. If we have T49.5 probe, you notice it does not say part 1 here. If it does not say part 1, it is implied then you are in part 2, the correct maintenance and manual for for working on the airplane. T4.9.5 probe removal would be covered under this task. So we have the information on how to do the work. We have references like open the thrust reverser. You can click that. It'll take you to that reference. Open the thrust reverser manual procedure. I recommend highly you do not do this. This is where you grab the thrust reverser and you just pull it open by hand. If you do this, you can trap air and into your actuators and you can't get your thrust reversers closed. You should always use the hand pump. There is a hand pump procedure. You should always use the hand pump procedure. Not use the pull it open by hand because you're strong procedure. So if you need figures, it gives you all the figures. So when you work on Boeing, you will have this nice hand pump. You will always want to use the hand pump to open these actuators. You want to hook up to this actuator and use the hand pump. If you do not use the hand pump, if you just grab the whole cowling and you pull it open by hand. I had a brand new 737-900 series. We had 2 of these actuators that got air trapped in them because the previous place that worked on the engines, they had pulled them open by hand. I don't know how they ever got them shut. We had to change 2 actuators on a brand new airplane because they were hydraulically locked so badly we could not get the cowlings closed again. So you always want to use the hand pump to open the cowlings. We want to go back. We say, oh, we were in the front of the book. What did we look at? Let's see if we get back to our home. So this history here, it shows these are all the things I looked at today during my login section. So if I can't remember what I was looking at before 3 hours ago, oh yes, of course. We were looking at the fan blades. Here's the reference right here. Bang, we go right to it and we're here. In task 72-21-00-200-801-F00. Power plant inlet fan blades inspection, general visual. This will be something you'll do on your overnight check. You just look for obvious damage on your fan blades. So you would do this task on just about a daily basis. You would follow these steps here almost every day that you're at work. If you want to do a more detailed inspection of it, then that's not general visual, that is detailed inspection. You might also do an NDT inspection, which is even more detailed. Hopefully someday we go back to working in school where we actually have the engine, and then we can take these manuals and go work on the engine that we have, but you'll learn how to work on a 737 by using the RB211. So if your plane is broken, your engine is broken, your axial flow CFM 56 engine is broken, you want to go first to your fault isolation manual. If you're on 737, you have something called troubleshooting manual, TSM, for A320. Same, but different translators making the book. This is written in American simplified technical English, and then Rolls-Royce has French engineers write the manuals and they get printed in Germany. So quite often the English that's in Airbus's manual, sometimes it's a little harder to understand. So if you have a fault, you have maintenance messages. 7710851. You get this from the CDU. There's a central computer display unit in the cockpit. It'll give you this message. You do a byte built-in test equipment, byte test from the cockpit, and it'll tell you 77-10851. It'll tell you have that fault message. So then you would have to find that fault message and what you would do to fix it. Notice you have related data, component location, simplified schematic. Simplified schematic manual is different from simplified schematic. Simplified schematic is something that's in the aircraft maintenance manual, where it's showing some of the components, where they're located. Simplified schematic manual is a different book than just simplified schematics. That's a confusing thing. Simplified schematic manual would look like this. In this case, we're only seeing wires. It's not showing us any components, just only the wires. Then we have our wiring diagram manual. In this case, that's going to look very much like the simplified schematic. But in the wiring diagram manual, we can find information. This wire, W018-0850-20, is a 20 gauge wire. It's 5 foot and 2 inches long. It goes from circuit breaker C01314, and it goes to a connector D40576 Juliet at pin number 11. For your project, you guys are going to have to use the fault isolation manual, wiring diagram manual, system schematic manual, aircraft maintenance manual, illustrated parts catalog, so you can show how you would troubleshoot a specific fault code in the airplane. So I'm going to give you help in terms of how to set it up so you can do this type of presentation. The goal is that not only will you pass the class, but you can take this material and you can give this presentation when you go for a job interview, and you can show that you know how to use the fault isolation manual and troubleshoot the airplane. I guarantee if you learn how to do this, even if you have no experience, you will get a job. Because most airline mechanics only remove and replace components without troubleshooting, which means 40 to 80% of the time they remove a component that there was no fault. It gets sent back to the manufacturer. The manufacturer does a bench check and says, no fault found. Sends the part back to the airline. Meanwhile, the airline has a fault in the airplane. 40% of the time that fault comes back because it was a relay, a wiring pin that was not secure. There was some fault in something like one of these switches. There are other things in the airplane that can fail besides just modules. It is break time. Who wants to take a break? Does anybody want to take a break?
Me. I want to take a break.
Okay, take a break for 20 minutes. I will see you in 20 minutes.
Okay.
Okay. Everybody is awake. Ready? Anybody out there? I think that's better. Okay, if everyone's
Ready?
ready.
Anybody there? There we go. All right. That's more like it. Now I know you guys are going to be awake. Okay, so we go back to the lecture notes again. And hopefully that works. So we're back in our module 15.4 compressors. This is on the 14th page of your lecture notes. Principles of operation. The impeller is rotated at high speed by the turbine. Keep in mind that your impeller is mechanically coupled to your turbine. Discussing centrifugal flow turbines again. So we are talking about engines that look like this. The Rolls-Royce RB41, Mean 10. We have our single stage dual entry impeller. It is mechanically coupled to our single stage turbine. This is made from 3 pieces. The curved sections are forged separately because it's easier to make it as 3 separate pieces with these curves. Turbine wheel has removable turbine blades. You can remove the turbine wheel, the turbine shaft, by disconnecting at this coupling. Our notes will refer to this coupling and then provide no illustration of the coupling. So construction of the compressor centers around the impeller, diffuser, and air intake system. The impeller shaft rotates in ball bearings and roller bearings. There will be roller bearings immediately in front of the turbine disc. The ball bearing will be at the compressor impeller. The ball bearing absorbs thrust loads. Roller bearings absorb radial loads. Roller bearings keep the whole turbine from coming out of the engine this way. Ball bearings prevent everything from going out the engine, out the front of the airplane. Centrifugal flow engine, it wouldn't be good to have the impeller try to go out the front of the engine because there is no intake on the front of an RB211. You have a gearbox in front of the impeller. Your gearbox has your starter, your generator, your igniter boxes. There's a hydraulic pump. There's 2 fuel pumps. So your impeller shaft rotates. You usually have 1 ball bearing, and then the rest are roller bearings. And can be either a common turbine shaft or a split shaft. So the split shaft, then you have a turbine shaft and a compressor shaft. They're separate. The 2 come together at a coupling, but as they're rotating in flight, they turn at the same speed. Impellers consist of forged discs. There should be no comma here. Consists of a forged disc with integral radially disposed vanes. So your vanes go out in the radial direction, but they're integral. It's only one piece. It's one disc. It's forged, one portion. But sometimes the vanes are fabricated in two separate sections. So you're taking the disc and then two other discs and attaching it together to make one single unit. It says the vanes may be swept, but for ease of manufacture, you'll have the vanes in the center of the impeller are curved in the direction of rotation, but they talk about straight axial flow. That becomes rather confusing because we're talking about a centrifugal flow engine. We're talking about the flow going this direction, then axially out this way, radially, axially this direction, radially this direction. So your airflow will flow this way. We're saying axially, and then goes radially out this direction. But you do have these curved tips. So this is manufactured separately from the center portion. The central portion right here, the vanes will be straight. The curved portion is fabricated separately as one unit. So it's a bladed disc. This could be termed to be a bliss bladed disc. You cannot detach. This is damaged. You cannot detach and replace only that one vane. You'd have to replace the entire impeller wheel assembly. The curved sections may be integral with the radial vanes or formed separately. As we have seen in the RB41 engine, they're formed separately to make it easier, more accurate manufacture. Since it's a forging, I don't see how you could make it with the curved sections being one particular component all by itself, because forging, you're taking heavy stamping die and you're slamming it in together, and you have to pound the part repeatedly. So being able to manufacture it in one piece with the curved sections, I think would be impossible. As it'd be possible as a casting, but as a forging, it would not be possible to make this. Impellers are normally manufactured from stainless steel or from the titanium. RB211, it ain't made from titanium. It's made from a really good quality stainless steel, but they didn't use titanium on RB211 RB41 engines. The impeller is not titanium. It's made from steel. Diffusers. The diffuser assembly may be an integral part of the compressor casing or a separately attached assembly. So the diffusers are elbows that will take the air from the compressor, gets compressed, and it comes out, rotates 90 degrees right before your combustion chamber. Your diffusers can be a one integral part of your case, or you can have them so you can remove them and replace them. They can be little elbows. You can unbolt them, remove them, replace them. For maintenance purposes, it's much better to have it separately attached assembly. Some of the very earliest jet engines, though, it was integral parts. You'd have just one big compressor casing, and the diffuser elbow was part of the one casting. They would make the whole thing as a casting. So if you damaged an elbow, then you'd have to do a welding repair, which means you disassemble the engine completely to be able to repair that one casing. The vane passages, this is in the diffuser, are divergent. They convert the velocity energy into pressure energy. The clearance between the impeller and the diffuser is an important factor because too small of a clearance will set up aerodynamic buffeting, and this could create unsteady airflow and vibration. This is a factor of design and of the engine. When it goes to overhaul, they will have to maybe grind the impeller to a certain clearance, so there'll be a gap between the impeller and the diffuser. As it's rotating, it will expand a little bit. They'll have to calculate it so that gap remains constant. You will not do this unless you're working in one of the only shops in the world that does this type of engine overhaul. I only know of one shop left in the world that you can send your centrifugal flow engines to for overhaul, and they're in California. And they're very expensive. It would cost $40,000 to $50,000 for an overhaul for a jet engine that you might have gotten for $4,000 or $5,000. Surplus. The diffuser converts the very high velocity air that's exiting the impeller. You convert the velocity into pressure. You convert your kinetic energy, the velocity, into potential energy, pressure. All of your compressors, you're doing this. You will accelerate your air. You gain an increase in velocity in your impeller or with your rotating blades. Blades, impeller vanes, they increase velocity. But then in your diffuser or your variable stator or your fixed stator vanes, your stator vanes, your diffuser vanes, you're slowing the gas back down, you're decreasing the velocity, but you're increasing your potential energy, the pressure. Because after all, your compressor, you're not trying to create velocity. Yes, jet engine, it makes you think you're creating velocity. You want to create pressure. Pressure gives you your potential energy, the increase in pressure and the increase in temperature. Remember this because people who write test questions, FAA, et cetera, I'm sure EASA questions are the same. They know most people are going to get confused and think the compressor is there to create velocity. It is not. So your diffuser or shroud is part of your centrifugal compressor section. For your centrifugal compressor to work, it's essential the clearance between the rotating impeller and the stationary shroud is adjusted to minimum adjust it to a minimum to prevent air leakage over the vanes of the impeller. Again, this is a function of overhaul. You are not going to do this as an A&P mechanic. You don't have the tools, you don't have the training, you're not certified to do this. This is more of a function of design and of your engine overhaul. As the clearances are very small, rubbing is commonplace. They say rubs. You could also say rubbing. It's commonplace between the two. Any rotating blade or impeller will brush against the stationary case or shroud. So then they create a function where the shroud is covered in like a sandpaper effect. So the abradable coating is a metal sprayed silicon aluminum spray. Basically what you do is you take molten metal and you spray it like it's a paint. And the person who does this, he has to wear a full body and enclosed respiratory mask because you can't breathe this stuff in. And he'll basically spray paint molten metal and it sprays on, and you end up with a very rough surface like a hard sandpaper. And as your blades or your impeller go by, they'll rub on there, and it'll cause you to lose some metal off the tips of your blades and off the tip of the impeller. So hopefully then while you're running, blades might grow a little bit, and they'll just barely come into contact with the case initially when you're running it in. And then eventually it gets to where you just have a very minute gap between the two of them, and the parts aren't supposed to be in contact with each other. When you do bore scope inspection, you'll go around your high pressure turbine shroud with a flexible scope. You'll go all the way around the whole engine, and you'll inspect the shroud to see if there's any areas where there's been heavy rubbing of the high pressure turbine blades against the case. It's normal to see this, but you make note of it, and then next time they do the overhaul, that one area where the blades may have been rubbing on the case, usually between 5 o'clock and 8 o'clock on the lower parts of the engine, the HPT blades, as they're going around centripetal force. If the blade is trying to go out the side of the engine, it's trying to become liberated free, it wants to exit through the case. The blade becomes a little longer as it's going down around 5 o'clock to 8 o'clock, and you'll see heavier rubbing down there. So when they grind the stationary case at General Electric, it would actually be an elliptical grind as you go down 5 o'clock to 8 o'clock, and they're grinding the case. So you'd have something that when you put the blades in, you'll have the engine run, and then the blades as they go around, they'll maintain the same clearance when they're hot. But if you took a feeler gauge down at the bottom, you have a much bigger gap than you would up at 12 o'clock, 12 o'clock, 10 o'clock, 1 o'clock. When you measure up there the clearance between the blades and the shroud, measure the clearance down at the bottom between the blades and the shroud, you have a much bigger gap at the bottom, because when the engine is running, it's almost like the blades are behaving themselves. And then when they get down here, they start to stretch out, get lazy, try to run away, don't pay attention in class, sleep. Is anybody paying attention? Probably not. The blades, as they go around down here, then a bit longer. Fan blades will do this too. When you get a job at the airlines and you have your fan blades in the front of your engine, if you inspect your shroud on the fan case, you'll notice on the bottom of the engine, you'll find areas where there's heavy rubbing of your fan blades. The big fan blades will rub on the shroud. You have to measure how much shroud you have left, because if you have less than 100 thousandths of an inch, let's say, on a JT9, it'll end up that as the blades are going by, you end up with a very large gap. And if you have static electricity, fly through a lightning storm, the plane gets hit, the fan blade will act like a spark plug. This will cause the fan blade to critically heat up to a point where it loses heat treat. And then the fan blade later on can shatter, and then you have an uncontained fan blade failure. Pratt & Whitney JT9 engines on older 747s, they had 2 engines where the fan blades disintegrated. They had uncontained fan blade failures. Fan blades exited through the fan casing. And they determined that this excessive gap between the fan blade and the fan shroud causes something called arc burn, where all the static electricity as the plane is flying, it would create a spark plug effect, and then basically get the blade to heat up so much that it was no longer acting as, let's say, a single crystal, became crystallized in different areas, created stress when the fan blade failed, shattered. Broken fan blade then starts destroying other fan blades, creates an imbalance. You have an uncontained engine failure. So, rubbing of blades on stationary shrouds, on casings, this is commonplace. So you'll find metal spray is what they will do. And they're creating basically a sandpaper effect on the shrouds. So as the blades go by, they'll sand themselves. It'll basically shorten blades a little bit. On your fan blades, however, your shroud on the fan case is not silicone. It's not designed to cause any abrasion or wear on the fan blades. In this case, the fan blade remains intact, remains the same length. The fan shroud material wears. It abrades away, gets damaged. Sometimes you have chunks of it break off. Then you have to do a repair of it. But if you end up with an insufficient gap, you end up with too big of a gap between the blade and the case, then you can damage your fan blades. This is something that's getting more attention now because we've had quite a few fan blade failures recently. But this has always been the case with high bypass turbofan engines, that the fans are the most critical thing that you have to keep an eye on, and then your high pressure turbine is the next most critical. Your compressor manifold is an air collection chamber. Often this compressor manifold is called your compressor scroll. Its function is to collect your air from the diffuser and turn it through 90 degrees via cascade vanes in the manifold elbows and direct it towards the combustion chamber. So this is what they're talking about. They don't show pictures here. Basically, this is what you're doing right here, is you're taking your air and you're rotating it through 90 degrees. So your impeller is rotating, your air gets accelerated, velocity increases, pressure increases, comes in axially, goes out radially. The air then goes to these diffusers. These diffusers act as a divergent nozzle. Your velocity is slowed down, pressure is increased because you have better energy from pressure, then from velocity. Then you're going to go through here and you're going to turn 90 degrees. This is your compressor scroll with your 90 degrees, and then from here you're going to go to your combustion chambers. Each one of these is going to a separate combustion chamber. I imagine there are 9 of these, because this is probably from a Rolls-Royce Nene 10. No, sorry, it wouldn't be because it only has single stage impeller. Rolls-Royce Nene 10 would have dual-sided impeller. So the air will come in, accelerate, and compress through here. As this is rotating then, they keep obsessing over the clearance. Keep saying you need to have a minimum clearance between your stationary casing and your rotating impeller. And they will put an abradable material on here. It will be abradable. So if you get a rub of the impeller as it's rotating, the impeller will wear. It will sand the impeller down. Your air then goes through here, makes a 90-degree turn, and will go to your combustion chambers. This part of the engine, to work on this part of a centrifugal flow compressor engine, even on experimental category engines, the FAA does not want people to take these engines apart because almost nobody has the correct tooling or training or spare parts to do that type of work. So that's an overhaul station that will do that. Going back to axial flow compressors. This is a Rolls-Royce Avon. The very good thing about this is we have this engine in the shop. We have a factory cutaway engine. You can go and look at this. It's in our hangar. This is one of the engines you get to work on during your lab. So we have a single spool compressor. So all of the rotating blades are all attached to one single spool. It all rotates together. It is built up of individual discs. Each stage with its blades is attached to a disc. The discs are all bolted together to make a spool. At every stage where you have the blades, you have a disc. In between each stage of rotor blade, you have stationary vanes. They say starter vane here. It should say stator vane, meaning stationary. Rotor blades rotate. Stator vanes do not move. This is a bleed manifold. Bleed air can come off of here for bleed functions. This main shaft back here, you can actually uncouple this engine. You can take the turbine out of the engine. If we so desired, we could do that. So we have these figures here on page 15. I'm going to go down and we'll see them in better detail. So this is our RB211 showing our stator, S-T-A-T-O-R, stator vane, rotor blade. We have an accessory drive that comes out the side to drive our accessory gearbox. And it's a single spool compressor. So in the cockpit, you would only have an N1 indication gauge. This is showing again that your velocity increases at each rotor blade. When you go across the stator vanes, your velocity will decrease. As your velocity decreases, your pressure increases. So velocity increase, decrease, increase, decrease. The net result is when you come out the back of the compressor, your velocity is the same as it was at the front of the engine. So whatever your flight speed is, your airplane's flying at 600 miles per hour, your air is going through. The goal is you don't want the air coming out the back here at 900 miles per hour. You don't want higher velocity air, you want higher pressure air. And the pressure back here would be about 180 psi. Are there any questions? Is everybody having fun? Is anybody awake? So here we have a figure that's not in your book. There is a file in the front of the file section in Microsoft Teams. You can download a book. It's RB211. Avon 524B general familiarization book. It's from Malaysian Airlines. So it has this drawing showing the cross section of a Rolls-Royce Avon. Like I say, we have this in the shop. And the compressor is a single spool compressor. This entire compressor all rotates as one unit, and it's made out of 16 stages of high pressure compression. In this diagram back here, you see blade number 15. However, for some reason, Rolls-Royce also has a stage 0. Maybe this was an afterthought. They'd already started designing the engine and already referred to it as being a 15-stage engine and decided to add a stage afterwards and have a stage 0. American engines, first stage would be called stage 1, not stage 0. We don't have stage 0 in GE engines. So they may refer to 15th stage air in the back, whereas actually they're after 16 stages of compression. Air coming out of what they call 15th stage will come here. The majority of it is going to go outside of your combustion chambers for cooling. 20% of the air will go through the combustion chamber and mix with fuel for combustion. Some of the air also can be drawn off through this elbow and be sent to the front of the engine for anti-ice. A company called Teddington makes this hot air valve, and it's for providing anti-icing to the nose of the engine, the inlet section of the engine. We have slide-type bleed valves. They have bleed valves where bleed air that comes in from the case will go through and come out. You have a cutaway in the shop. You can also look at this. In the turbine engine shop, you have the cutaway of the engine, and you also have a cutaway showing how these bleed valves work. So every disc in this high pressure compressor is a separate disc, all bolted together to form one spool. More modern engines, like in GE, will have a stage 3 through stage 9 spool to where it's one big drum with slots in it for multiple sets of different blades for stages 3 to stage 9. Then you have one big drum assembly. It's called a compressor spool, and then it saves weight because you don't have all these discs. It reduces the amount of metal you need to build the engine. In the front, you have the starter spline shaft going into the front of the compressor. So for this engine to rotate the compressor, you are directly taking the starter into the front of the compressor. So you're turning the compressor and all 3 stages of the turbine. You're turning everything all at once. You'll notice that some of the bleed air goes down through the shaft, cools the inside of the shaft, provides pressurization for oil sumps. We have a roller bearing right here. Further up, there is a ball bearing. The ball bearing absorbs the shock loads axially along the engine, the shock loads. Roller bearings absorb radial loads. So radial absorption of loads is what's needed back here. You're keeping your turbine nice and centered, no vibration. And back here, they very unusually call this high pressure, intermediate, and low pressure. These terms on the RB211 will mean 3 separate rotors. In this case, we have 3 discs that are all physically bolted together. They're bolted together here and here. This all rotates as one assembly. There's higher pressure, intermediate pressure, and lower pressure, but you will not find this terminology is used on any other single spool engine, because this will confuse you, because RB211, the HP spins at a different speed, faster speed than the IP and the LP. They all turn at different speeds because they're not mechanically attached. These are mechanically attached. It's one assembly. And we can remove, we can come to the coupling right here. We can come through here. We can disconnect the coupling. We could remove this entire turbine unit. But we would have to also unbolt the flanges, because we'd have to remove the stators and rotors all as one big assembly. So this whole assembly in the back would all be something we could remove as one unit. I don't know if we really would need to have any special tooling to do that. I don't have the manuals to show us how to do it. In the future, perhaps. So here we come out of our compressor. The air will then go through the combustor. 20% of the air goes through the combustor, mixes with fuel. The other 80% comes out here and cools combustion chamber liner and comes through and creates pressure to keep the flame centered. You do not want the flame to hit combustion chamber liner. The flame will then come through and it will hit your stationary high pressure turbine nozzle, HPT nozzle. These vanes are not air cooled. Also, your high pressure turbine blades are not air cooled. They do not have passages for the air to go through and cool them. On your Rolls-Royce RB211, your CFM 56, those blades and these vanes, the first stage vanes are air cooled, and then your HPT1 blades are air cooled. They have hollow pores and they're drilled with holes, laser drilled, and you run cooling air through those to keep them from overheating. We have an alternator on this engine. We do not have an integral drive generator. They have a fuel-cooled oil cooler. The fuel will cool the oil. Also, this helps warm the fuel to prevent icing. You do not want ice to form inside your fuel system, like your fuel nozzles. You don't want them to clog with ice. So earlier we were looking very briefly at how you can have a 3-spool axial flow engine. Low pressure compressor, intermediate pressure compressor, high pressure turbine. This is the RB211 like we have in the hangar. So remember, our low pressure compressor is mechanically coupled to our low pressure turbine. Our intermediate pressure turbine is mechanically coupled to the intermediate pressure compressor. This is a shaft. This is a very large diameter shaft. So one is hollow, the other one rotates through it. There's a ball bearing for each one of these stages. The ball bearings are at the front of each rotor to absorb thrust loads. Ball bearings are more expensive, heavier duty. If this ball bearing fails and this seizes, then your fan shaft will break. If the fan shaft breaks, back here you have roller bearings to absorb the axial loads, but there is no roller bearing behind the ball bearing here. So if the fan shaft breaks, now your fan shaft will be unsupported. So if you have excess of radial loads, then what will happen is all of your low pressure turbine blades will shatter end up with little pieces of metal rolling out the back of the engine. And you'll come to the engine and you'll see the fan blades spinning in the wind, because now it can spin freely. There's nothing holding it. But your low pressure turbine is completely shattered, destroyed, melted. The stators are shattered, and the LP turbine blades are a complete mess. And usually your blades are only this tall when they used to be this tall. So you do not want to have a failure of your roller bearing, but it does happen. So if you have a failure of the roller bearing, then you would hope that your fan speed is governed by sensors that monitor the fan speed. When General Electric originally built the CF6-80 series engine for the Airbus, they put sensors on the low pressure turbine for speed. So if the low pressure turbine was not turning fast enough, the response was to put more fuel into the combustion chamber. More fuel in the combustion chamber logically means you would have higher speeds in your turbine. Your combustion gases are going to come in contact your HP turbine, which is mechanically coupled to your HP compressor. They turn together. This is not going to break ever. You won't have a separation between HP compressor and HP turbine. But you can have the LP turbine fan shaft break right here, snap right here. I've seen 3 engines do this. One on wing at Continental. I got to see a GE90 that failed. And when I worked engine overhaul at General Electric, I got 2 engines that came in that this had happened, that this bearing had failed and it broke the fan shaft. When 787 was first coming out, they had a flight developmental engine. The fan shaft broke on the ground, and then they found that they had cracks in 1 or 2 more of the engines that hadn't flown yet. So they had to do some modifications. They did an ultrasonic inspection by going into the engine with a probe and doing an ultrasonic inspection for cracks without disassembling the whole engine. So if your sensor's back here, your fan shaft breaks, your LP turbine is going to slow down. Actually, no, what they do is they put the fan shaft sensor, they put the sensor only on the fan blades. The fan shaft broke, so the fan sensor here was saying, oh, we need more fuel to get more thrust back here. So what happened was that the engine just kept putting in more and more fuel and eventually over-temped the entire turbine area, melted the blades, caused catastrophic failure, particularly in the low-pressure turbine. And what happened on that engine was, on wing, on an Airbus engine, is the entire engine melted and broke into 2 pieces and was hanging off of its respective mounts. In the back of the engine, there was a mount, and on the front of the engine, there was a mount. CF6-80, they put the mount back here, so this part of the engine was hanging on one mount, and then the forward fan area was hanging right behind the fan frame that was hanging on the forward part of the pylon, and the entire engine in between had separated into 2 pieces. So they didn't make any compensation to look at a situation where the fan shaft would break. So it was only looking at the fan speed and saw the fan was slowing down, so it dumped more fuel into here and overtempt the engine. On your RB211, this is what it would look like. You'd have this shaft with the disc. You can remove the disc from this fan shaft. So the fan shaft is attached to the fan disc. This will go back through the engine and will go connect to your low pressure turbine. So this is what your fan blades are going to look like. This is your intermediate pressure compressor. The fan was considered low, like a low pressure stage of compression. Now you're going through here. This is intermediate compressor. This is the full compressor with stators and rotors. You'll notice that these right here, there's a linkage, set linkage. These are variable. These are fixed vanes. These are variable vanes. They could either be called variable stator vanes, but most of the time, if they're in front of the first stage of rotating blades, these would be called variable inlet guide vanes, VIGV. They're basically stator vanes that they have a linkage The linkage is a unison ring. Every vane moves at the same time. The angular change is the same for every single one of these. If you had a vane that was out of schedule, this linkage broke and you had one vane that wasn't turning with the others, you would have a catastrophic failure of the engine at this point. So you want to make sure that they all have the same schedule. They're all turning at the same rate. Your variable inlet guide vanes and variable stator vanes are very critical in terms of engine reliability, because they control the flow of the air through the compressor. More closed at startup, takeoff power, then they'll be fully open, allowing more volume of air to pass through the engine. And remember, as always, you're not looking for an increase in velocity of the gas, you're looking for an increase in pressure. So we go from very tall blades here to very short blades in the back. We have a convergent duct. Convergent duct. It's getting smaller towards the back. So we have an increase in pressure. We also get an increase in temperature. So this is the intermediate pressure module on the RB211. That is this part of the engine. This is your N2 right here. We have a ball bearing here. There is a roller bearing at the front. There is a roller bearing here right behind the fan. Your ball bearings are back here, main ball bearings, the thrust loads, and roller bearings here for axial loads. Low pressure, only the fan blades. Intermediate pressure, you have these stages, 1, 2, 3, 4, 5, 6, 7. Intermediate pressure compressor. If you're going to borescope these, you have to reach past where the fan is. You have to turn these with a mechanical tool to actually grab the blades and turn them. We want to borescope the intermediate pressure. High pressure compressor, you would use a drive shaft that comes up from the gearbox. You would use a ratchet. You'd be able to rotate only a high pressure compressor and high pressure turbine rotor. So you can inspect the 6 sets of rotor compressor blades. You can inspect 6 stages of compressor blades and 1 stage of turbine blade. High pressure turbine, intermediate pressure turbine, low pressure turbine. 3 sets of blades on the low pressure turbine. Each one is progressively larger. This is a divergent duct. So now we are having a decrease in pressure. We want to try to convert all of our pressure energy into mechanical energy to spin the fan as efficiently as possible, because the fan is creating 80% of our thrust. So the actual energy of the exhaust gases coming out back out here is not as important as what we can extract from these 3 stages. If we could add a 4th stage of low pressure turbine here, it would be even taller. This might create us a more efficient fan, get more energy out of the fan. The exhaust gas that does come out of here still does have energy. So now they take this, and this is now, again, the convergent duct is going to squeeze the air to try to create more pressure again. So we've gone all the way through here, increase the pressure some more, come through and have our combustion, and then as we're going back here, we're not increasing pressure now, we're decreasing the pressure, but as we're decreasing the pressure, we're trying to get the reward back from our investment that we put into it. We want to turn that pressure into mechanical energy. Then as the exhaust gases that do come out, we try to squeeze it in the back, try to get a little bit more thrust out of the engine there. But this thrust is only 20% of the thrust. When RB211 was initially made, as well as General Electric CF6 series engines, they initially had thrust reversers, where the engine would head towards takeoff power after you touch down, you're on the ground. Thrust reverser sleeves come back, but blocker doors then will take the air coming from the fan and blow it forward, reverse the thrust. RB211 and CF6-6 and CF6-50 engines, they initially had blocker doors. They had a thrust reverser on the core of the engine. But they determined that for the weight of this system, about 850 pounds, with this only being 20% of the thrust of the engine, they found that having that blowing the air forward didn't really make as much of a difference in terms of the wear on their brakes and the landing ground roll. So they deleted the turbine reversers that they had on these engines, both on RB211 and on CF6 series engines. The intermediate module, they show an intermediate module here. It's in between the two. This is mainly a location for bearings. We have two of our roller bearings inside of here. And we also have this radial drive shaft that's going to go down to our gearbox. You're doing the borescope, you're rotating this shaft, which then in turn rotates the compressor. Then our HP module, this section here, contains our high pressure compressor. High pressure compressor, 6 stages of rotating blades. Then we have our stator vanes, and then we have 1 stage of high pressure turbine blades in the back, 1 stage of HPT. So that's what our high pressure module looks like. When you do your borescope on RB211 out in the shop, you're mostly going to do most of your borescope on this part of the engine, because you can go to the accessory gearbox and rotate this, which is your N3 rotor. You'll notice it has a very large diameter opening in here. You're going to have both shafts pass through this. You'll have your intermediate pressure connect. The compressor will connect to the intermediate pressure turbine to here. And then through the middle of that will be your fan shaft going from the low pressure turbine to the your fan shaft, which is basically your low pressure compressor. So this is your low pressure, intermediate pressure turbine module. So inside this one casing, you have 2 separate turbines. They will turn at separate speeds. They can even go in separate directions, rotational directions. So one could be turning clockwise, the other counterclockwise. Since they are only aerodynamically coupled, it doesn't make any difference which way they rotate. Since there's no mechanical connection between the two, there's no gears, there's no drive shafts, there's no connection, no bolts, no screws, nothing. Yes? Anybody? Question? No question. Okay. So anyhow, this part right here, this would be going into your intermediate pressure compressor, and then this right here would go forward. It would attach to your fan disc in the front, which is basically your low pressure compressor. LP compressor case. This is your fan case. This is the entire big case on the engine. When you go in, you guys are always standing in this to get pictures. Everybody loves to stand in here. When you take the fan blades out, part of your project, you're going to remove the fan blades. Going to be upstanding in the inlet. In a real engine, you would want to put some pads in there to protect the inlet from being damaged, because you have your stationary shroud sections there that the fan blade, they're called acoustic panels. They help to deaden some of the noise in the engine. You don't want to puncture those. So if you're up there working with your tools and you're not protecting them with a mat, you can damage your LP compressor case shrouds. These are stationary vanes. You'll have to reach back through here and turn your intermediate pressure compressor by using a tool. You're going to go through there, and you're going to have to turn your intermediate pressure compressor. It's the only way it will rotate. Nothing mechanical drives the intermediate compressor, and the intermediate compressor also mechanically doesn't drive anything. They're connected, only the turbine is connected to the compressor, and they're not connected to any gearbox or anything else. Your gearbox looks like this, and you'll go through the front here with a ratchet, and you'll rotate here, and then that will rotate your high pressure compressor, high pressure turbine. But the intermediate pressure compressor does not connect to this. So there's no way to connect to mechanically turn the intermediate compressor from the front or the back of the engine, except for going to the front with a tool that you'll take and you'll grab the blades and pull the blades by. You can't do that by going to the back. You would have to remove all of the high pressure turbine blades. There's 3 stages of them. You can't do that on the flight line. 747 has this exhaust in the back. It looks really cool. We don't have that from our L1011 engine. We don't have an exhaust like this. We just have a normal looking cone. This one is supposed to be to make the engine look quieter, sound quieter. It just makes it look cool. We would normally have a generator on our engine. We do not have a generator when we got our engine here. We don't have a generator. Effectivity, South African Airways, 003 to 006. So this particular diagram only covers that airline's RB211 engines on a Boeing 747-400. The 747s I'm going to work on do not have Rolls-Royce engines, unfortunately. They almost all have General Electric, which I'm very familiar with. I used to overhaul CF6-80 C2s. One of the engines I used to work on was from what they call Air Force One, a BC-25A. I used to overhaul engines for the Air Force as well as for commercial operators. But we do have quite a few things here on our engine that are the same as the 747 engine, such as our fuel system. A lot of the components are the same. We do not have a FADEC, however. This engine has FADEC, the RB211-524G and RB211-524H did have FADEC, Full Authority Digital Electronic Control. We do not have FADEC on our engine. Even if we had it, it probably would have kept the FADEC computer because it would have been worth more than the engine. This would be our starter. We also do not have a starter on our engine at school. We do have, going through the starter drive pad, we do have a ratchet for turning the high pressure compressor, high pressure turbines. So we can turn them to our starter drive pad. And really quickly, we will show this beautiful Rolls-Royce drawing. We have our air inlet. We don't have all of this at CATC. We do have our LP section, IP, HP compressor section, LP, IP, HP. Combustion section. Then we have our turbine section, HP, IP, and LP. Mixer and integrated exhaust unit. No, we don't have that. We just have an exhaust cone. We don't have a fancy. Our velocity, you'll notice it does fun things here. Up and down, and it goes up, and it comes down, up and down, up and down, up and down as we go through. And it does come out the back at a slightly higher velocity than it went in. Came in at about 550 feet per second. Going out the back, it looks like it's about 575 feet per second. Sorry, temperature of degrees, it's not 500, about 1,500 feet per second. So we didn't get a lot of velocity increase to here. This is the important thing to notice, is that the velocity here is almost the same as the velocity in, slightly more velocity, but you'll notice it sharply goes up right here, sharply increases the velocity. So the velocity is being increased because of your converging ducting in the exhaust part of the engine. So the way that they design the ducting, the cowling around the engine, you're getting a velocity increase after the air has left your turbine. So your exhaust section, your ATA 78 section, is where you're going to get the big velocity increase. The engine itself, your compressor, combustor, and turbine do not really increase the velocity very much. It's not its goal. Even though it does increase in certain areas, you're trying to trade off that and decrease to gain a big spike in pressure. So you see your pressure goes and then rapidly jumps up, spikes up, and your temperature as well. So as you compress it, you're increasing your pressure and your temperature. Then when you mix with your fuel, it'll sustain a good, nice, clean burn. More pressure increase, more temperature increase. Then you take that energy as you go through the turbine area, and you're dropping your velocity back down in exchange for mechanical energy. Then the exhaust system creates that last little bump up in velocity to give you some more thrust, but that's a function of the exhaust. It is probably a good time for you guys to think about going and doing homework or going to sleep. Is anybody awake? Anybody paying attention? Do you want to keep going? You want more lecture? More? More? Yes? No? More lecture?
Who wants to go have dinner? Who wants to go to sleep? Yes? No. Good night, engineer. Good luck. Adios. Go to sleep. Good night. Good luck. Hope you're ready for the exam. Everybody
Hello,
ready for the
teacher.
test?
Do you hear me?
I can hear you.
Okay, teacher.
Lecture is finished. Go home. Sleep.